This video is on using the first and second derivative to sketch the graph of a function. So we'll use the previous material that we've got, the domain and range of a function, the first and second derivatives and what they say about increasing and decreasing functions and concavity, as well as previous information about limits and vertical and horizontal asymptotes. So for each of these problems, we're going to do the following. We're going to give the domain of f of x. Remember that that's the set of all possible input values such that f of x is defined. So we'll first give the domain, then we'll take the first and second derivatives to find the critical numbers, places where the first derivative is equal to 0 or does not exist. We'll find where the function is increasing or decreasing using the first derivative and also find any relative maxes or mins. We'll determine where the function is concave up and concave down and any inflection points using the second derivative. We'll identify any vertical or horizontal asymptotes, and then we'll sketch the function based on all of this information. And we'll plot key points such as x or y intercepts, and the points found above, including relative and absolute maxes and mins and inflection points. So let's use this to sketch the graph of x to the fourth plus 2x cubed. So we'll use this to sketch the graph of f of x is x to the fourth plus 2x cubed. So first of all, what's the domain of this function? The domain of this function is all real numbers. Because this is a polynomial, and anytime that we're talking about a polynomial, any input that we put into the function has a defined output. So the domain here is all real numbers. Now let's find the first and second derivative. So our first derivative is 4x cubed plus 6x squared, and our second derivative, f double prime of x, is 12x squared plus 12x. All right, so to find the critical numbers, the places where our first derivative could be equal to 0 or does not exist, here f prime of x is 4x cubed plus 6x squared. This exists for all values of x. So now we want to figure out where are the places where the first derivative is equal to 0. 4x cubed plus 6x squared equals 0. We're setting it equal to 0 and solving it for x. So we could pull a 2x squared out of both of those terms. 2x squared times 2x plus 3 equals 0. And that factored form tells us that either x is equal to 0 or solving for x, in this other term, x is negative 3/2. So those are our two critical numbers. And now we can figure out the places where the function is increasing or decreasing by plugging in values in between those critical numbers. So we're plugging it into the first derivative, f prime of x. Now we want to plug in values in each interval, so we could put in 1 is a number greater than 0, negative 1 is a number between the critical numbers negative 3/2 and 0, and negative 2 is a number less than negative 3/2. So we can pick any number in those intervals, but those ones are easy ones. So f prime of negative 2, that's 4 times negative 2 cubed, that's 4 times negative 8, plus 6 times 4 times negative 2 squared. So that's negative 32 plus 24. That's less than 0. So we're negative down there. The function is decreasing. F prime of negative 1 would give us, f prime of negative 1 is 4 times negative 1 cubed is negative 4 plus 6. That's greater than 0. So we're positive over here. And f prime of positive 1, well, that's going to be 4 times 1 plus 6 times 1, that's greater than 0, so it's positive over here. And so now we know that the function is decreasing, so f of x is decreasing on the interval from negative infinity up to negative 3/2, and increasing on the two intervals from negative 3/2 up to 0, as well as from 0 to infinity. But the first derivative is 0 at 0, so it is neither increasing nor decreasing at that point. We can also use this to find some relative maxes and mins. So because the function is decreasing before 3/2 and increasing afterwards, that means there is a relative min at x equals -3/2. So let's plug in f of -3/2 into the original function. F of x is x to the 4th plus 2x cubed. So f of -3/2 is -3/2 to the 4th power plus 2 times -3/2 cubed. And when we plug that in the top, we've got 81 over 16 plus 2 times 27 over 8. That's a -27/8 since that was cubed. And if we simplify that, that simplifies that whole sum to -27/4 if we do some getting a common denominator and adding fractions and simplifying. So we have a relative min at the point -3/2, comma, -27/4. So we've got a relative minimum at that point. And we know we're increasing and decreasing over those intervals. So that'll all be useful for us when we're graphing the function. All right, so now let's think about concavity. Let's think about our second derivative. Our second derivative is 12x squared plus 12x. So f double prime of x is 12x squared plus 12x. And again, we're going to set that equal to 0 and solve for x to find the places that are potential inflection points. So here we can factor out a 12x. So 12x times 12x plus 1 is 0. And so that gives us two potential inflection points of x equals 0 and x equals -1 are potential inflection points. Now to determine concavity, we can look at the number line of the domain for f double prime of x for the second derivative and separate that number line by the potential points of inflection and plug in points into the second derivative. We can plug in -2, -1/2 is the number between those two values, and +1 is a number in between those values into the second derivative into f double prime of x. So we saw that was 12x squared plus 12x, or 12x times x plus 1. And sometimes it's easier to do it right into the factored form to see whether it's positive or negative at those points. So for f double prime of -2, that would be 12 times -2, that would be a negative, times -2 plus 1, that's also a negative, so that's going to be greater than 0, it's going to be positive. F double prime of -1/2, so 12 times -1/2 is negative, but -1/2 plus 1 is positive, so negative times a positive, that's going to be less than 0, and f double prime of 1, that's going to be 12 times 1 is positive, and 1 plus 1 is also positive, so that's greater than 0. So we're negative here, positive here, the reverse. We are positive here, we're greater than 0 over that interval, we are less than 0 over this interval, and we are greater than 0 over this interval. So that tells us the concavity over these intervals. We could also plug in and find the exact values, but again, all we need to know is whether it's positive or negative. So what we now know is that we are concave up over the interval from -infinity up to -1, as well as the interval from 0 to infinity, and we're concave down over the interval from -1 to 0, and this also tells us that we do have two inflection points because we have two places where the function changes concavity. So we have inflection points at x equals -1 and x equals 0. So let's plug into our original function f of x equals x to the 4th plus 2x cubed to find those exact inflection points. F of -1 is negative 1 to the fourth power plus 2 times negative 1 cubed. So that's 1 minus 2, that's negative 1. And our other inflection point is f of 0. That's going to be just 0 in this case. So our two inflection points, the two places where the function changes concavity, are at negative 1 comma negative 1 and 0 comma 0. So those are our two inflection points. So we know where the function is concave up and concave down, and we know where our inflection points are. So the next piece of information we're asked for is whether there are any vertical or horizontal asymptotes. So remember that there is a vertical asymptote. That's a place where the limit as x approaches c of f of x is positive or negative infinity. So a vertical asymptote is a place like that where as x approaches c, the function either goes to positive infinity or negative infinity. And again from the right or from the left. We could have a horizontal asymptote. That's a place where the limit as x goes to infinity of f of x is some constant k, or the limit as x goes to negative infinity of f of x is some constant c. They could be different asymptotes in theory. So a horizontal asymptote is one that occurs if the function approaches some value as x approach if the output of the function approaches some output as x approaches infinity, and it could be that they both have the same asymptote on different directions, or going to positive or negative infinity, or they could have different ones. So that's a horizontal asymptote. So do these occur in this situation? So here our function f of x is x to the fourth plus 2x cubed. So first of all, let's say, does it have any horizontal asymptotes? Well, the limit as x goes to infinity of f of x is just going to be positive infinity, right? As x gets large, the output is just going to get infinitely large. And the limit as x goes to negative infinity is also going to be positive infinity as well, because we've got x to the fourth positive value overtaking that negative value. So since this is not going towards a finite number, so there's only a horizontal asymptote if as x approaches positive or negative infinity, the output of the function approaches a finite number, so no horizontal asymptote. What about, could there be any vertical asymptotes? Well, vertical asymptotes are going to occur where, if there's some point not in the domain. And so since the domain of f of x is all real numbers, is negative infinity to infinity, there's no vertical asymptotes either. So anytime we have a polynomial, there aren't going to be any vertical or horizontal asymptotes in those cases. All right, now let's sketch the function based on the information that we've got. So we know the domain, we know where it's increasing and decreasing, where its relative maxima and minima are, where the function is concave up and concave down, and its inflection points. So let's start by plugging in just the points we know. So we know we've got an inflection point at the point 0, 0, as well as the point negative 1, comma, negative 1. So we've plotted those. And we know that we've got a relative min at negative 3/2, comma, negative 27/4. So that's negative 1.5, comma, negative 6.75. So here is that point approximately, right there. So negative 1.5, comma, negative 6.75. Let's see, are there any other points we'd like to know about? Well, one thing we asked for was intercepts of the function. So one intercept is just, what is the y-intercept of the function. F of 0 we already know is 0. Our function is f of x is x to the fourth plus 2x cubed. We could also, that's our it's both our x and y-intercept. We could also look for whether there are any other x-intercepts. Those are places where the function output is equal to 0 is on the x-axis. So to solve for x, we could have x to the third pulled outside, x to the third times x plus 2 equals 0. And so that gives us x equals 0, which we already know, as well as x equals negative 2. So those are our x-intercepts. So we've also got this point right here, 2 comma 0. So, all right, so what's going on with this function? We've got that it is concave up over the interval from negative infinity up to negative 1. So it's concave up this whole way. And we kind of can see what the function must be doing. It must be doing something like this and being concave up over that interval. So that's that negative 1.5 point down there. And then it's concave down over this short interval from 1 to 0. So it's concave down right there, concave down. And then it is concave up again from 0 to infinity. I think it'd be nice to have one other point after x equals 0. So let's plug in f of 1 to see what that is. F of 1 is 1 to the 4th plus 2 times 1 cubed. That would give us 3. So the output of f of 1 is right there. And as I said, we're concave up here, so our function must look like that because it just continues being concave up and never shifts to being concave down. So this is our sketch of the function f of x equals x to the 4th plus 2x cubed. It's not a perfect graph, but it's got some important points on it. It's got the x and y intercepts. It's got the inflection points 0, 0, and negative 1, negative 1. It's got, this is actually our, not just relative, but also our absolute minimum. And that is our function.